Hello, I'm Luis Serrano and this video is about Generative Adversarial Networks, or GANs for short. Developed by Ian Goodfellow and other researchers in Montreal, GANs are a great advance in machine learning and they have numerous applications. Perhaps one of the fanciest applications of GANs is face generation. If you go to this page, thispersondoesnotexist.com, you'll see it in action. These images you see here are of people who don't exist. They have been fully generated by a neural network. This is fascinating considering how detailed their expressions are. In this video, we'll learn how to generate faces with a GAN in a very simple way. And great news for those of you who like to sing along to the videos as you type code. In this video, we'll be coding a pair of one-layer neural networks which will generate some very simple images, and it's all on GitHub under this repo, which you can find in the links. But if you don't want to write code, this video is for you as well, since we developed the intuition and the equations by hand as well. First, let me give you a general idea of what GANs are. GANs consist of a pair of neural networks that fight with each other. One is called the generator and the other one the discriminator. And they behave a lot like a counterfeiter and a cop. The counterfeiter is constantly trying to make fake paintings and the cop is constantly trying to catch the counterfeiter. The counterfeiter is the generator and the cop is the discriminator. So as he gets caught by the cop, the counterfeiter keeps improving and improving his paintings, until one day he learns to finally paint a perfect one that completely fools the cop. In neural network language, what happens is that we have a pair of neural networks, the generator and the discriminator, and we train them with a set of real images and a set of fake images generated by the generator. The discriminator is trained to identify which images are real or which ones come from the generator, and the generator is trained to fool the discriminator into classifying its images as real images. In this video, we'll build a very simple pair of GANs. So simple that we'll be able to code them straight in Python without any deep learning packages. This is our setting. We live in a world called slanted land, where everybody looks slightly elongated and walks at a 45-degree angle. This world has technology, but not as developed as ours. They have computer screens which display images, but the best resolution they've been able to work out is 2 times 2. So they have black and white 2 pixels by 2 pixels screens. Also, they have developed neural networks, but only very simple ones. As a matter of fact, they only know neural networks of one layer. But I will show you that in this simple world, we can still create a pair of GANs that will generate faces of the people who live in slanted land. Here are 4 faces of people who live in slanted land. Notice that everybody is elongated and tilted 45 degrees to the left. Since the screens are only 2 pixels by 2 pixels, this is how the pictures of the people look in the screen. They mostly look like a diagonal or a backward slash. And this is how noisy images look. Notice that these are not faces, since they don't look like a backlash, and these are mostly generated randomly. So the goal of our networks is to be able to distinguish faces like these from noisy images or non-faces like these ones. Let's attach some numbers here. We'll have a scale where a white pixel has value 0 and a black pixel has a value of 1. You may have seen this in the opposite way, but we'll do it like this for clarity. This way, we can attach a value to every pixel in the 2 times 2 screens. Okay, we're ready to build our networks. First, I'll build them by hand, and then I'll show you how to get the computer to train them. Let's start by building the discriminator. The first question is, how are we going to tell faces apart from non-faces? Easy. Notice that in the faces, the top left and the bottom right corners have large values because their pixels are dark, whereas the other 2 corners have small values because their pixels are light. On the other hand, in noisy images, anything can happen. Therefore, the way to tell faces apart is by adding the 2 values corresponding to the top left and bottom right corners and subtracting the values corresponding to the other 2 corners. In faces, this result will be very high, whereas in noisy images, it will be low. For example, for this face, the value is 2, and the value for the noisy images minus 0.5. We can add a cutoff or a threshold of, say, 1, and say that any image that scores 1 or higher is a face, and any image which scores less than 1 is not a face, or is a noisy image. In neural network lingo, this is how things look. The values of our 4 pixels get multiplied by plus or minus 1 depending on what diagonal they are on, and then we subtract a total value of 1 or the bias. We add these 4 numbers, and if the score is 1 or more, then the image is classified as a face, and if it's less than 1, that is classified as not a face. In this case, the image is a face because it gets a score of 1. We can also output the probability that something is a face by using the sigmoid function. We apply the sigmoid, which is this function that sends high numbers to numbers close to 1 and low numbers to numbers close to 0. And we get sigmoid of 1, which is 0.73. This discriminator network then assigns to this image a probability of 73% that it is a face. Since it is a high probability, greater than 50%, we conclude that this discriminator thinks that the image is a face, which is correct. Notice that in this neural network, the thick edges are positive and the thin ones are negative, and this is a convention we'll be using throughout this video. Now, if we enter the second image, which is not a face, into a discriminator, then we do the same calculation and we get negative 0.5 for the score. Sigmoid of negative 0.5 is 0.37. This is lower than 50%, so we conclude that this discriminator thinks that this image is not a face. The discriminator is correct again. Now, in the same way, let's build a generator. This is a neural network that will output faces. To build a generator, we'll again take into account that among faces, these 2 corners are high value, these 2 corners are low value, whereas in noisy images or non-faces, anything can happen. So this is how the generator works. First, we start by picking an input z, which is a random number between 0 and 1. In this case, let's say it will be 0.7. In general, the input would be a vector that comes from some fixed distribution. Now let's build a neural network. What we really want is to have some large values and some small ones. The large ones are represented by thick edges and the small ones by thin edges. Because remember that we want large values for the top left and bottom right corner and small values for the top right and bottom left corner. So since the top output has to be large, we want these weights coming in to be large. So let's make them plus ones. Now what do we get for the output here? Well, first we're going to get a score of plus 1 times 0.7 plus 1, which is 1.7. Now let's look at the second node. It corresponds to the top right corner, so it has to be a small value. So let's put negative numbers here. What do we get for the score? We get minus 1 times 0.7 minus 1, which is minus 1.7. In the same way, we want a small value here, so we put weights of minus 1, and we get minus 1.7. And for the last one, we want a high value, so we put plus 1s, and we get plus 1 times 0.7 plus 1, which is 1.7. Now those are just the scores. We need to apply sigmoid to find the probabilities. So we apply sigmoid and we get 0.85, 0.15, 0.15, and 0.85. Those are the values that will go in our pixels. And notice that our image looks like a diagonal, which is how we define our faces. Notice that by the way we built it, this neural network will always generate large values for the top left and bottom right corners and small values for the top right and bottom left corners, no matter what value z we input, because remember, z is between 0 and 1. Therefore, this neural network will always generate a face. That means it's a good generator. Of course, we built these neural networks by eyeballing the weights, but that's not how it's normally done. In general, we have to train the neural networks to get the best possible weights. For this, let me tell you a little bit about error functions. An error or cost function is a way to tell the network how it's doing in order for it to improve. If the error is large, then the network's not doing well and it needs to reduce the error to improve. The error function that we'll use to train these GANs is the log loss, which is the natural logarithm. This is the logarithm base e. Why the logarithm? Well, logarithm appears a lot in error functions for many deeper reasons which we'll not cover, but we can think of it for now as a very convenient function. Let's first say that we have a label of 1 and our neural network predicted this as 0.1. This is a bad prediction and we should produce a large error because 0.1 is very far from 1. On the other hand, if the label is 1 and the prediction is 0.9, then that's a good prediction because the prediction is very close to the label, so this should produce a small error. How then can we find a formula for this error? Well, notice that the negative natural logarithm of 0.1 is 2.3, which is large, while the negative logarithm of 0.9 is 0.1, which is low. As a matter of fact, the closer a number is to 1, the smaller its negative logarithm gets. Therefore, when the label is 1, the function negative logarithm of the prediction is a good error function. Now let's go in the other extreme, when the label is 0. In this case, if we had a prediction of 0.1, it would be good because it's close to the label. Therefore, the error should be small. On the other hand, a prediction of 0.9 is terrible, so the error should be large. The function that we need here is similar to the previous one, but with a slight difference. It is the negative logarithm of 1 minus the prediction. Notice that in the first case, the error is the negative logarithm of 0.9, which is 0.1, and in the second case is the negative logarithm of 0.1, which is 2.3. And this matches what we wanted, which is that the first error is small and the second is large. To summarize, if the label is 1, which means we want the prediction to be 1, we define the log loss to be negative logarithm of the prediction. Notice that from the graph of negative logarithm of x on the right, this is big when the prediction is close to 0 and small when the prediction is close to 1. And then when the label is 0, which means that we want the prediction to be close to 0, then we use as an error function the negative logarithm of 1 minus the prediction. From the graph of negative logarithm of 1 minus x in the right, we see that when the prediction is close to 0, there's a low error, and when the prediction is close to 1, there is a high error. So these two are the error functions that we're going to use for training the generator and the discriminator based on if we want the prediction to be 0 or 1. Now that we have our error functions, we get to the meat of our training process, which is backpropagation. I will explain it very briefly. The way we train a neural network is by first taking a data point and performing a forward pass, calculating the prediction, and then calculating the error based on the log loss that we previously defined. Then we proceed to take the derivative of the error based on all the weights using the chain rule. This will tell us how much to update each weight in order to best decrease the error. The way we reduce your error using a derivative is a process called gradient descent. Long story short, what you do is you plot the error with respect to the parameters, then calculate the gradient, which is the direction of greatest growth, and then take a tiny step in the direction of the negative of this gradient in order to find new parameters that decrease this error as much as possible. Now we're ready to train the generator and the discriminator, and what we have to do is put the right error functions on the right places. Here's our pair of neural networks, and notice that the weights are not yet defined. So we start by defining them as random numbers. Now we select Z as some random number between 0 and 1, which is going to serve as the input to the generator. We do a forward pass on the generator to obtain some image, which is probably not a face since the weights are random. This is going to be our generated image. Now we pass that generated image through the discriminator so the discriminator can tell if it's fake or not. The discriminator outputs a probability. So let's say that it's, for example, 0.68. Now pay close attention because this is where the rubber meets the road. This is where we define the correct error functions. First, let's think. What does the discriminator want to do here? In other words, if the discriminator was great, what should it output? Well, since the image is not a face, but it's a generated image from the generator, then the discriminator should be saying that it's fake. That means that the discriminator should be outputting a 0. If we remember the error function, the way we measure an error when we want the neural network to output a 0 is the negative logarithm of 1 minus the prediction. This is an error that will help us train the discriminator. Now that we've figured out what the discriminator wants, let's go to the generator. What does the generator want? Well, the generator's wildest dreams are to generate an image so good, so real that the discriminator classifies it as real. Therefore, the generator wants this whole neural network, the connection of the two, to output a 1. That means that the error function from the generator is negative logarithm of the prediction. So that is the error function that will help us train the weights of the generator. In other words, if g of z is the output of the generator and d of g of z is the output of the discriminator, then the error function for the generator is negative logarithm of d of g of z, and the error function from the discriminator is negative logarithm of 1 minus d of g of z. The derivatives of these two are what will help us update the weights of both neural networks in order to improve that particular prediction. Notice that these two error functions fight against each other, but that is okay because the red error function only changes the generator weights and the blue error function only changes the discriminator weights. Therefore, they don't collide. They simply improve both neural networks as one to produce different outputs, which is fascinating. So what we have to do now is repeat this process many times. We pick a random value for z, we apply the generator to produce a fake image, apply the discriminator to that image, and use backpropagation to update the weights on both the generator and the discriminator. Then we take a real image, plug it into the discriminator, and update its weights again using backpropagation. So what happens after many of these iterations or epochs? Well, we left the training in the notebook and we got these values for the weights. To make it easier, I've drawn thick edges for the positive weights and thin edges for the weights that are negative or 0. Feel free to pause the video and convince yourself that these two neural networks actually work really well. Both the generator for generating realistic looking faces and the discriminator for being able to tell apart the faces from the non-faces. And the reason for this is that if we remember from the beginning of the video, the top left and bottom right corners of a face should be big and the other two should be small. So let's just convince ourselves. Let's look at the generator. Notice that since the input is between 0 and 1 and the two top edges are positive, then the sigmoid value of this output is large, which is the value of this pixel over here. Therefore, that pixel has a large value. Similarly, these two values are also positive and they give us a large value for this pixel over here. Now these two over here are negative, so they give us a small value for this pixel, and these two over here are negative, so they give us a small value for this one. And therefore, our image looks a lot like a diagonal. And given the resolution of the screens in slanted land that are all 2 pixels by 2 pixels, then this picture looks uncannily like this resident of slanted land over here. Thus, we have built a network that generates faces. Now, as promised, here's the code for you to sing along to the video. It's in this repo called GANs under my GitHub. First, we have the faces that we hard code and the random noisy images that we generate that are not necessarily faces. Then, we also develop the derivatives carefully for the discriminator based on faces, then for the discriminator based on noisy images, both with respect to the weights and with respect to the biases. These are all coded in this discriminator class. We also work out the derivatives corresponding to the error functions for the generator, again with respect to the weights and the bias, and these are all coded in the generator class. We also have error function plots. We can plot the error function for the generator and the error function for the discriminator. Notice that the generator error function goes down and stabilizes, but since the generator ends up fooling the discriminator, then the discriminator error function doesn't do so well and actually goes up at the end. And finally, we ask our generator to generate some random images, and here they are. Notice that they all look like faces in slanted land, which is what we wanted from the beginning. Therefore, we have successfully created a pair of GANs that generate faces in slanted land. Now, time for some acknowledgements. This video would not be the same if not for the help of my friends, so a big thanks to Diego, Sahil, and Alejandro who helped me in various ways, either encouraged me to learn GANs more seriously or helped me with endless questions or gave me great feedback on my code. Diego in particular has a great series of blog posts where he codes GANs from scratch in PyTorch and TensorFlow. I use them as an inspiration for this video, so I highly recommend them. And that's all for today. I hope you've enjoyed it. I'd like to remind you that I have a machine learning book called Grokking Machine Learning, in which I explain the concepts of machine learning in a down-to-earth way with real examples for everybody to understand. In the description, you can find the link to the book and a very special 40% discount for the viewers of this channel. And as usual, if you enjoyed this video, please subscribe to my channel for more content, or hit like, or share amongst your friends. And feel free to write a comment. I really enjoy reading your comments, especially those with suggestions for future topics. And if you'd like to tweet at me, my Twitter handle is LewisLikesMath. All the informations, videos, writings, etc. can be found at this link, serrano.academy. So check it out. Thank you very much for your attention, and see you in the next video.